Hi, I'm Shanawaz. In last lecture, we were discussing rational functions on projective variety. So, if we have a projective variety, say x, so this is a projective variety. So, this is a projective variety, and let Ix be the homogeneous ideal of x. So, this is the homogeneous ideal. Then we can define the coordinate ring of x, I mean the homogeneous coordinate ring of x, which is denoted by Sx, and it is the quotient ring of the polynomial ring in n plus 1 variables modulo the homogeneous ideal. Then we saw that if we denote by this big F, the class of little f, where f is I mean this is some element of x, with this little f being a polynomial in n plus 1 variables, then we have the degree d part of f, which is denoted by f of d, and it is actually the class of degree d part of this little f. Now with this notation, we can define the degree d part of Sx, and that is given by Sxd, where it contains elements of the form f of d, where f is an element of Sx. Now, x being the projective variety, this Ix is a prime ideal. So Sx is an integral domain. So it makes sense to talk about the quotient field of Sx. So the quotient field of Sx, I mean the Q of Sx. So this is called the field of rational functions on X, and it is given as, so this is given as, it is denoted by Kx. It contains all rational functions of the form f over g in the quotient field of Sx, I mean such that f and g they are I mean f and g they belong to the degree d part of Sx. Otherwise, this will not define a function on x. So here we take f and g to be in the degree d part of Sx for some d. Now we are going to define the local ring at a point P of a projective variety. So we have a definition. So let us consider X to be the projective variety. This is the projective variety, and let us take some point P in X. So let P be any point in X. So then we can define the local ring of X at P. So the local ring of X at P is the set. Actually, it is the ring which we denote by OXP. So it contains elements of the form f by g, I mean the rational functions on X, uh, such that g evaluated at P is different from 0. So this set is a ring, so it is not hard to prove that this is a ring, and this ring is called the local ring at the point P. Now, if we take a quasi projective variety, for example, if we take an open subset, say U of X, so for U subset of X, so let us take, if U is an open subset, the ring of regular functions on U, the ring of regular functions, the ring of regular functions on U is the subring. So it is a subring O. We denote this set to be the set OXU, which stands for the hmm, ring of regular functions on U. So it is actually the intersection of all local rings at point P, where this intersection runs over all points in U. So one can prove this is a ring. So again, we will view OX U as a set of functions from U to K. So let us make a remark here. A regular function let us take the function h in OXP. So this is a sorry, OXU. H is given to be regular on U. So this defines the function. So this defines a function h from the open set U to the underlying field K, which takes a point P in U to the element H evaluated at P. So which is same as, because H being a regular function, it's a rational function, so we can write H as the quotient of f and g for some polynomials f and g. So for some f and g, so to make this a function, this f and g, they must belong to the same degree d part of Sx. So they are in some degree d part of Sx. So otherwise this will not define a function. So with this h is actually the rational function f divided by g, with g of p non-zero, because h is an element of OXP. So in the same way as in the affine case, we see that the function is a well-defined and identifies OXU with the set of functions from the open set U to K with the following property. So in the same way as in the affine case, we see that this defines a well-defined function. From the set OXU to the set of functions from U to K. So we have this correspondence OXU to the set of functions from U to K. So this is a well-defined function. This function is well-defined and identifies OXU with the set of functions with the set of functions h from u to k with the following property. Now, what is the property? So, I mean, the property is that for any point, so if we pick any point P in X, there exists an open neighborhood. Open neighborhood. We use NBD as a shorthand for neighborhood. So there exists an open neighborhood, say W in X, and homogeneous polynomials and homogeneous polynomials, say f and g in the polynomial ring, of same degree, with g being non-zero on W, with g non-zero on W, such that this h of q is same as f of q divided by g of q. So this is true for all q in W. For all q in W. Now we have one more remark. So, so I mean a rational function. If I take a rational function in OXP that determines the corresponding function u to k and vice versa. That is, if we are given a function from u to k, that function is determined by some polynomial, some element in OXU. So a rational function or a regular function on u. So a rational function, say h in OXU. So this function is determined by, so this is determined by the corresponding function from u to k. So thus, if we are given two regular functions on u, so then if f and g are the elements of OXU, so they give the same functions on an open subset W of u if they are equal as elements of the regular functions on W. So then, so if they give same functions on an open subset w of u, then they are equal as elements of regular functions on w. So this is actually a subset of kx, and thus as elements of oxu. In particular, they define the same functions from u to k. From u to k. Now we have some properties of regular functions. Let us call this a proposition. So the first item of this proposition is that the constant functions, I mean all elements of K, are regular on any open subset U of X. So constant functions, I mean if we view the elements of the underlying field as the rational functions, so they are regular. So they are regular on any open subset U of X. Not only that, if we take two regular functions on U, then their sum and product is also regular on U. So, moreover, if f and g are regular on U, then their sum and their product uh, are also regular on U. I mean, they are the elements of OXU. Not only that, so in addition, if G uh, is non-zero on U, then the quotient F mod G, F divided by G, is also an element of OXU. So also if G is non-zero on U, then the element F mod F divided by G, F mod G, is also an element of the regular functions on U. The second item of the proposition is that, so let us take an open cover of U. So let say U sub I be an open cover of U. So if function f from U to k is regular, so I mean then uh, a function say f from U to k is regular. Let us call this h here. One can note that we can identify this function h as an element of OXU. I mean the a regular function on U. So then the function is regular if and only if uh, if we look at the restriction of H to each UI. So this restricted function must be regular. So this is regular for all I. Or we can restate this statement. So I mean, or H from U to K is regular if and only if for all points P in U there exists a neighborhood, an open neighborhood, say W, such that F restricted W is regular. So one can see over here these two statements are same, because if we pick any point P in U, and if we look at the corresponding neighborhood of P, which is W in this case, so these W's, they will give us an open covering of U. So these two statements are the same statements. So let us prove these. So actually the first the first item of this result is trivial, because we know that the set OXU is a ring. So now OXU being a ring implies that all constants are regular, as well as if we have two elements, say F and G in OXU, then their sum as well as product is also an element of OXU. So this follows from the fact that the set OXU is a ring. So by definition of OXU, so by definition of OXU, which is the intersection of all local rings at P, where the intersection runs over the elements of U. So therefore, it is enough to show that for if F and G are in the local ring at P, then their sum and product. I mean, therefore, it is enough to show that uh, so therefore it is enough to show that if we have two elements, say F and G, in the local ring at P, then the sum and the product are also the elements of local ring of X at P. So we skipped this part. We didn't prove here the constants are the regular functions, but we know that uh, I mean we know that if I look at the coordinate ring AX, this is the local ring of X at X. Now this being a K algebra means that this contains K as a subring. Now if that is the case, that means all the constants are also elements of uh, this this set. But uh, that means all the constants are regular functions. So this is the one way to prove the constants are regular functions. And other way is that we can view every constant. So if we have a constant a in K, then we can view this constant as a over 1, where um, this a and 1 are the polynomials, the polynomial ring. Now one being I mean one is nowhere 0 on any open set of x. In particular, one is non-zero on u, so that means a divided by 1 a regular function of is a regular function over u. So that is trivial. So this is trivial. So if f plus g, if f and g are the elements of OXP, then the sum and product, they are both elements of OXP. The reason is that the set OXP is actually a ring. So this follows from the fact that the local ring of X at P is a ring. Now to prove the quotient f over g is in the local ring of U, so we are given that g is non-zero everywhere on U. So now since uh, g has no zero in U, this would imply, so then 1 over g is an element of the local ring at P, because g is nowhere 0 inside U, hence it is non-zero at P because P is an element of U. So for this is true for all P inside U, or this means or this means 1 over g is a regular function on U. Now using this part here, so f is an element of OXP, 1 over g is an element of sorry, f is an element of OXU, 1 over g is an element of OXU. Then using the fact that their product is an element of OXU will give us the desired result. So therefore f times 1 over g, which is same as f divided by g. So this is an element of OXU. I mean, this is regular on U. So this follows from this fact. I mean, part second of the item first. Now, to prove the second item, so second item is also trivial. So one can note that. So h from U to K. So this is regular if and only if h is in the local ring at P for all P in, I mean, for all P inside U, but UI being an open cover of U, we see that H from U to K is regular if and only if H is inside OXP for all P inside UI and for all I. So this gives us the desired result. Now we have I mean an important result here. So a proposition which says that if we take a projective variety or the affine variety, so if x is inside an or x is inside Pn, so be a closed subvariety. So if we take an open set in X, so this is open, and h is any regular function on U, then h from U to K is continuous with respect to the Zariski topology on An. So then h from U to K is continuous. Uh, with respect to the Zariski topology on the space. So we have K to be the affine one space. So this space is given the Zariski topology. So this is given the Zariski topology. So with respect to this topology, every regular function on U is continuous. So let us prove this. So a map H from U to K, so this will be continuous if we restrict this map to any neighborhood of any of its point, and that restricted map must be continuous. So indeed, if we if we take the map H from U to K, so this is continuous if it is a restriction to our neighborhood of each point, say P in U, is continuous. If we have the open set U here, so if this H is continuous on U, then if I take any point P inside U and if I look at the open neighborhood of P, then if I restrict this H to this neighborhood, that is called this W, then this restriction map is also continuous. So thus we can replace U by such a neighborhood. So we can assume, so thus actually this is if and only if condition. So thus I mean by replacing U by such a neighborhood, we can assume that this H of Q is F of Q, is the quotient of two polynomials, and G of Q with F and G being polynomials, so they are the polynomials, and in projective case they are of same degree, so they are of same degree in the quasi-projective case. In the projective case, so where f and g are polynomials. So we can assume h of q is f of q over g of q for all q inside u. So now with respect to Zariski topology on K, the closest sets of K are the empty set, the K itself, and all finite sets. So with respect to the Zariski topology, the closed sets of, I mean, with respect to Zariski topology on K, which is same as the A1, the closed sets of the affine one space R, the empty set, the affine space itself, and the finite sets of A1. So now to prove this H is continuous, we need to prove that the inverse image of any closed set in K is, I mean in A1 is closed. Now if I look at the inverse image of this empty set, that is empty, and empty set is closed. Similarly, if I look at the inverse image of A1, then that is U, and U is closed with respect to the subspace topology on U, which is induced from the Zariski topology on A1. And finally, we have to prove the inverse image of finite sets is also closed. That is, I mean, it is suffices to prove if we prove that inverse image of any singleton set is closed. So note that H inverse of the empty set is empty, which is closed in U with respect to the subspace topology on U induced from the Zariski topology on A1. I mean the set X. So this is closed in U, and the inverse image of the affine one space, which is U, is also closed. Thus, it remains to prove the inverse image of finite sets in A1 are closed in U. Now, to prove the inverse image of finite sets in A1 are closed in U, it suffices to prove the inverse image of any singleton is closed. So it suffices to prove H inverse of a singleton set A is closed for any A in A1. Now, if I look at the inverse image of A, we have now H inverse of A is the set of all elements in U whose image under Q is inside is A, which is Q inside U, but H of Q is same as f of q divided by g of q. So that is f of q is equal to a times g of q, or this is the set of all the elements in U such that uh, q f minus aq of, sorry, a g of q is 0. That is the zero set of the polynomial f minus ag intersection with u. So one can note that this is a closed set inside u. So this is closed. So hence h from u to k is continuous. So one should keep this in mind, that whenever we have a regular function on, uh, I mean, we have a regular function on u, then the function h from u to k is continuous. I mean, the corresponding function.